So let's now derive the equations that determine the interior structure of a star. If you consider the amount of mass in an infinitesimal volume element, you derive the first equation, which is the equation of continuity of mass. So let's see, you have infinitesimal of mass, called the dm, which is the density times the differential of volume. In spherical coordinates, then you have that this would be equal to rho r squared sine theta dr d theta d phi. Now, if we consider spherical symmetry, then we can integrate it in solid angle. It leaves only the dependency in radius. So if you assume spherical symmetry, you have then that the mass of a shell, let's call it dm, is then the integral in solid angle of the differential little m. And now I'm making a difference between what a differential of little m would be. So say that you have a sphere and consider a shell in that sphere. The differential of mass little m would be a single patch in here of width dr and extent r d theta. And then it also has a dimension in azimuth that I'm not showing here. So that would be the differential mass dm. The differential mass big dm is the integral of all of the azimuths and all of the meridional angles, but keeping it being infinitesimal in radius. That's what this integral here is saying. Big M is the shell, little m is just the infinitesimal volume in the 3 dimensions. So if you integrate to this, using the expression for d little m is equal to rho r squared dr times the integral then in solid angle, sine theta, d theta, and d phi. And of course, the integral in solid angle is 4 pi. So that gives you 4 pi r squared rho dr. If we divide both sides by dr, then we have the mass continuity equation. The mass continuity equation tells you the mass of each shell, how the mass in each shell is varying with the distance. As you see, it's simply a function of the radius and the density.